So we've got several options for what we're going to use as our basic modeling unit. And the first one that we're going to look at is kind of the most obvious one, which is words. Okay. Now I need to make just a quick distinction between word types and word tokens. So word types, if you've done machine learning, this is like the different types of classes that you have in your problem. So this is the set of unique words, or maybe the vocabulary in the language. Okay? And then the tokens are the instances of words of a specific type. So you can have multiple word tokens of the same type occurring in a text. Okay, does that make sense? In image classification, you would have a model, one of the model class outputs would be cat, but you can have many images, many different images with cats in them, different cat tokens, all belonging to the cat class. Okay, so this is the first test that you're writing in this course. It doesn't count. How many word types and tokens are in this sentence? Is a type, cat is a type, and is a type. We've already got that one. Brown, dog, chases, we've already got that one. Black is one, and we've already got dogs. Okay, so there's 7 unique words, yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 tokens. Okay, cool. Okay, types, unique words, tokens, like how many instances of words do you have? And my aim here is just going to show you that words aren't nearly as obvious as we think they are. There are some nice things about words in the sense that there are things across languages that holds with respect to words, but then there are also things that makes words actually quite tricky. Just as a little example, in 10,000 sentences from the English Wikipedia dump, which is this data set that I used, there are this many word tokens from this many word types. So you've got 200,000 word tokens coming from like 25,000 different word types. Okay, and then if you count up on this data set, you count the occurrences of the word the occurs a lot. Okay, so I call that the rank 1 word. It's the word that occurs most common. Of and to is as that, the and that, and you can see in this case I actually maintained my capital letters there, so the in the beginning of a sentence looks different from the somewhere in the middle. Okay, but you're starting to see something here already, like the word that occurs most often, it really occurs a lot compared to its like even its closest competitor, right? It's almost half. And we'll see that in a second. If we just look at the nouns for this data set, then you end up with this little table: Apollo, state, Lincoln, Alaska, time. Okay, and you can see that these words actually, like 419, compared to determiners like the and it's actually a very small number. Okay, and you can also see that I probably scraped I used the first file in the Wikipedia scrape because all these things start with A. So it's probably like early on in the data that I looked at. Now, there's this very interesting observation that holds across all languages. And this is that the frequency of a word is inversely proportional to its rank. Okay? So what this means is that you have few words that occur a lot. Okay? So the number 1, 2, 3, 4, 5 words in that ranked list occur way more than most of the other words. And you've got this relationship that the frequency of a word is inversely proportional to its rank. Okay, and this is called Zipf's law, and you see this actually in many different settings. Let's just look at Zipf's law here in action. So this is again that Wikipedia dump that I just looked at, and here we've got the rank on the x-axis and then the frequency of the word on the y-axis. And here we've got the word here. What word is this? That's the most common word. Okay, and you can see that, well, it occurs, like if you normalize it by the number of words in the data set, it occurs a lot compared to the others. I think this is the word of, okay, and so on. And what can you see here already? That most of the words in my language occurs once, twice, maybe 3 times. Okay, and the bulk of the words in English actually only occurs a couple of times. Okay. Now Zipf's law, the other cool thing is that if you plot it on a log-log scale, then it turns into a linear plot. Okay. So the frequency of the word is inversely proportional to its rank with some constant, C. And if I take the log on both sides, this is grade 1 mathematics, then you get log F, this is Y minus X, and then some constant here. Let's just do it K. Okay, so you get this straight line going down on the log-log scale. So here we've got log, and here we've got log. These words all just occur once, okay, and these words all occur twice, okay, and then you've got this linear slope here, and you've got the word, this is the word the, this is the word of, and this is the word and. Okay, cool. Let's look at the Wikipedia dumps of a few other languages and see what the log-log zip plot looks like. Here we've got the English plot, the frequency and the rank. Here I've got Afrikaans, okay, and it looks suspiciously similar, okay. Here we've got isiXhosa, here we've got isiZulu, okay, and you see this rich gets richer type of situation across different languages, in the sense that the rich, these words, they just get used way and way more than the words you write at the bottom in the tails. Okay, this is maybe something that could be useful for us to know, but it poses a massive challenge for natural language processing systems. Why? So when we're building an NLP system, we want it to work on language, okay? But by definition, the words that you see most of the time will be words that you've maybe, if you're lucky, you've seen once or twice in your data set. Most of the words you've only seen once or twice in your training data, okay? Sometimes you've never seen them, okay? And we need to actually deal with that extreme sparse case where we have 0 count words, okay? So that's exactly right. Sparsity is a huge problem in NLP land, okay? And specifically if you're using words, you will, by definition, be getting inputs that you haven't seen before, or that if you're lucky, have seen once or twice in your training data, and now you need to deal with this. This isn't the end of our pain and suffering when it comes to words, okay? You might think that the idea of a word is obvious, but it's not the case, okay? So even in English, where words are okay-ish, you have things like didn't. I don't know, is that 1 or 2 words? I'm not sure, okay? New York, not sure. High risk, at Stellenbosch University, if you're on Twitter, okay? So that's in English, challenges that you might face. Other languages like German and Afrikaans, they use agglutination a lot, which means that you take 2 words and you just, when you're writing them out, one thing, one word is the rule in Afrikaans, right? So you end up with words like satellietnavigasiestelsels, really, really long. K-gemiddelde trosvormingsalgoritme, that's K means clustering in Afrikaans, for some reason, okay? Computer linguistic Vorlesung, which is the German for NLP lecture. That poses a major challenge when you start to glue words together. Afrikaans speech recognition is quite tricky because it's very difficult to know whether I should write them as separate words or one thing. My final year project was written in Afrikaans, and the longest word in the project was no band telefoonspraak databasisse. Right? It took a line to write. Okay. This isn't the end of our troubles. Languages like isiZulu and many of the indigenous African languages spoken in South Africa are morphologically rich languages, which means that you're gluing together things called morphemes. These are minimal units of meaning that you're gluing together in order to modify a word or actually to build up a word. And we'll look at morphology in just a second. And then I've already mentioned Chinese, which is, or Mandarin. They don't put spaces between words. Okay? So this is an example from Jarofsky and Martin, where you've got the sentence here, which is translated into this. And a native Chinese speaker has said, okay, well, you can break this up into words if you want to, but there are several different ways in which you can break it up. Okay? So maybe you keep the names as one thing, and this, but you can also break up the name, and reaches, and so on. Okay, but then you can actually break up all these characters into little units that make sense. If you're writing in Chinese, which uses these characters, which corresponds to morphemes or syllables, then it's not as all clear where to put the word boundaries, okay? And a native Chinese speaker would be able to tell you just immediately what's going on in the sentence, but for an NLP system, it might get quite tricky. I should say for Mandarin, there are other writing systems that uses the Latin script now, so that you don't need to deal with these characters. But if you want to build a Chinese NLP system, the good thing to do is probably to actually try and deal with these characters. We've looked at words. That's kind of one option. We've looked at characters. That's another option. Okay, and they have benefits and disadvantages. Okay, words are nice because in many languages you can split them at the word boundary, they've got a lot of structure. If I show you one word, you can probably get the meaning from that. But we have this massive sparsity problem that you're going to have to deal with words that you've seen once or twice or 0 times in your training data. On the other extreme, you've got something like characters. Characters are in a sense useless because if I give you a single character, you can't tell me anything, right? There's no meaning attached to a character in isolation. But we don't suffer from a sparsity problem as much. There's only 25, 26, or maybe 40 characters if I include some special characters. So I will see all the characters in my training data and I can go on with life. But maybe there's something in between these two extremes of words and characters. Okay, and I've actually already mentioned one of them, which is morphemes. Okay, morphemes is not words. A single morpheme can be a word, but it's basically little subword units that we can maybe use as the input to our NLP system.